So throughout today, we'll be drawing some diagrams, and these diagrams are going to be basically how we'll communicate information about bonding. So the diagrams are not optional. Make sure that you're drawing some things that we speak of as you go, okay? So the whole idea of bonding is kind of bizarre. We're like, well, okay, we know things bond. We know they're covalent and ionic and metallic. But there has to be some sort of reason why two atoms get together. So the reason behind it is all related to stability. And you guys mentioned that a little bit whenever you were looking at like the stable electron configurations with your ions and with different atoms within our last unit. And also yesterday. Where did you see the word stable yesterday? What did we do yesterday? You guys saw that we kept seeing the word stable. Shout it out, come on. The little gizmo thing, right? The simulation kept saying, oh, this ion's stable now. This ion's stable now. Well, individually, those ions may have been stable, but they actually still have to stay together. That's an ionic bond, and that's what the whole theme was for yesterday. So the reason it's stable is because just like two atoms separate, and this was in the covalent tutorial, this atom here by itself is actually really high energy, and it's very unstable by itself. And this atom over here is high energy, and it's very unstable by itself. And the reason that it's unstable is because it doesn't have octet or duet. So I'm going to add the word duet here, the duet rule, and that's generally just for small atoms like helium, hydrogen, helium, lithium, beryllium maybe. But there's a couple things that are just so small, they don't really get to attain octet very well. They actually do duet, which is two valence shell, or two electrons in its valence shell. So when these two high energy atoms come together, they share electrons or they donate electrons, they form a bond and that actually stabilizes them. They actually get to lower their energy and become stable. So a good example of this is thinking about how reactive things are by themselves. What was the fun fact I shared it with you about sodium, just individually sodium by itself? Some type of water, say again? Sodium by itself explodes in water, right? It is incredibly fiery. I don't know if there's an electron there. It's explosive, but it catches water on fire. Sodium by itself, right? What kind of information do you maybe you already know about chlorine gas? It's poisonous, right? They used chlorine gas in wartime, chemical warfare, and they did that because they didn't want people to survive, right? It's toxic. But when we take individually sodium and put it individually with chlorine, they make sodium chloride, which we call salt, right? Table salt. But is it explosive in killing us? No. No. So they totally change their characteristics to super crazy reactive to something that's like, tasty, right? So we have this like reactivity thing we have to deal with, but when they bond, they're actually better off. So they're bonded in an ionic situation and they're better off. They're more stable. It's like a good relationship, right? You don't want your crazy self and some other crazy self being crazy. You want to come together and have a happy relationship with somebody. We can talk about that later. Okay. So this comes together in three ways really, but we specifically work with ionic and covalent most commonly. We won't really be drawing metallic bonds situations so much. Okay? Moving on from here. Okay. So this is kind of my version of the chart. So that's why I wanted you guys to have it printed so you could add a couple of details to this. So if you don't have it printed, write it down until you can get it printed. So I'm going to highlight a couple of things that I think are important. You've already got how it bonds, creates, electrons are transferred, where they create ions, right? Ions, ionic, that kind of goes together. The electrostatic force is probably already on there. Electrostatic just basically is like a magnetic attraction where you have positive attracted to negative. Keep going across the ionic side of things. We know it has a lattice structure, and that's a crystal. The lattice structure is a crystal. So it's a very strong structure. You probably already have solid at room temperature, high melting points and boiling points. This is not news to you, right? All this stuff is good. Yes or no? Okay, it's on your charts. The one thing you maybe didn't have on your chart is usually water soluble, meaning whenever you drop, I'm actually going to maybe add this over here. When you put do not take a picture of this right here. I'm videoing right now. And if you didn't do your chart, you didn't do your chart. Okay? Okay. So when your two ions come into water, they actually can dissolve. So I drew them separately as sodium ion and chlorine ion. And that's dissolved, meaning that it's going to now have a different characteristic than normal. This actually gives it that characteristic of conductivity in molten, right? And this is what your warm-up was regarding. When they dissolve, they are conductive in molten or aqueous solution. Only because this characteristic of ionization, when the ionic compound comes in the water, it ionizes and it can allow electricity to flow through it really, really well. So, do you drop your hairdryer in the tub when you're in the tub? No, because your salty body would then allow for the electricity to come through the hairdryer to you because the salt water is conductive. But if you had pure water, pure H2O, no ions at all, and you drop the hairdryer in the water, what would happen? Water, H2O by itself, it supposedly doesn't have any ionic concentrations, so it won't have any flow of electricity, so you should be safe, right? But let's not do that. So, because your body still has salt in it. All right, so we'll talk with the lattice energy section later, but it's just regarding the strength of the compound itself. They are very, very strong bonds because of this magnetic attraction. But water just can rip it apart. It's so strong, we say, but water can pull the ions apart and make these two separate ions. It's kind of crazy on the nanoscale how things work differently than for the macro scale. Okay, so for covalent, so there's just a couple of extra features I want you guys to add. We already know they share electrons, but we're going to start to draw diagrams regarding covalent molecules, water being one of them. So I'm going to draw water here. Here's the formula. It actually looks like this. So it's got this kind of bent shape to it, like that, and you maybe even seen it like this before with like two H's like this off the side, big O. So you've seen these structures, but they actually have shapes. You don't realize it, but this is a bent shape. This bent shape, we're going to talk about why we draw it bent, maybe probably tomorrow, but there's a theory behind it. There's always a theory behind everything, right? And it's called the Vesper theory, VSEPR. The Vesper theory can help us predict the shapes of molecules that are covalent molecules. So I just might add this little piece right here. I'll tell you what Vesper means too. Valence, shell, it's in your reading guide. Valence shell, electron, pair, anybody? Repulsion theory. Okay, valence shell, or valence shell electron pair repulsion theory. That's what Vesper stands for. And what does that actually mean? Well, this little diagram that I've drawn here, I've drawn two dots. Those dots are actually electrons. And these electrons up here, what kind of charge do you think electrons have? Negative, right? So there's like a negative charge up here, a negative charge up here. This line actually is representing two shared electrons here and here. So this is a negative charge as well. This has a negative charge as well. What can you tell me, what do you think is happening between this negative charge and this negative charge? Right, two negatives don't like each other, so they repel. So instead of being a flat shape like this, the water repels its arms down to give it a bent shape. So that's the Vesper theory. We're going to talk about that a lot. The other terms that are here, and I wrote from my highlights, is the word volatile. Okay? Raise your hand if you put deodorant on today. What? You put deodorant on. Nobody, everybody's got their hands up. Okay, smell it? Okay, smells good, right? Alright, so why does it smell good?
They made it.
Well, it's a solid, right? Can you normally smell solids?
What?
No.
No, deodorant, most deodorants, they can do the aerosol cans you spray in your arms, or like a solid stick and you rub it on your arms, right? Okay, how do you normally smell solids?
Yeah.
No. Can you? I don't really smell this.
Smells like pencil.
I don't smell it. Sometimes it smell like your pencils.
Right, but what's in it? Like, is there a solid coming up in your nose and going, hey, smell me? What's coming into your nose to make you smell? Gases, okay? So I smell cucumber, melon, okay? Why?
That's made of cucumber.
But that means there's gases coming off of my underarm into my nose and says, nose, you smell cucumber melon. Why?
Because something in the deodorant.
Something in the deodorant
Creates that smell.
changed to a, what'd you say?
What does that create that smell?
Or change your gas.
Changed to a gas. Okay, but how is it changing to a gas? It's under my arm.
The heat from it,
The heat, okay. So give me more. Really in.
the
pressure.
heat, and
Oh yeah. It smells. No, the pressure from your arms aren't gonna do anything. I'm not squeezing the deodorant out of my arm. It's making it
I
smell.
think that kind of.
the
Makes it into liquid and then evaporate.
Okay, so your hot bodies are making your deodorant basically evaporate, and then it hits your nose, and you're like, I smell good. Okay, if there was nothing in your deodorant that would vaporize easily, you'd smell like BO. Okay, you smell like your body odor, which comes from the bacteria that lives on you. So if anybody ever says you smell bad, just say it's my bacteria. They're having a bad day, because it's not you, it's your bacteria. They're the ones that are pooping and making gases on you. It's not you. So the word I'm talking about, like vaporizes easily, is the word volatile. Okay, the word volatile just means vaporizes easily. And if you don't have things that vaporize easily, like in your deodorant, you're not going to smell good. Okay, so a lot of things that make you smell good are things that have an odor to them, just have a covalent molecule in them, and that covalent molecule is going from solid liquidish state to gas pretty easily. Yes, sir.
So like when I'm like doing stuff and I like smell or like I'm playing basketball or something, that's like, how does that apply? Like is there bacteria growing as you're playing or like I don't know.
So there's bacteria that grow at a rapid rate, given some nutrients, and if you don't control them by like washing them away, they tend to build up. And many times that happens on like gym clothes because you're rubbing things more vigorously, and then they start to build up and compact more. So that's why they have a little bit of a stain to it. Okay, all right. So that's it right now for covalent. Okay, we're gonna draw some structures now. So, this is the picture I just wanted to show you. You guys probably drew this already on your chart or something similar. It was like positive, negative, positive, negative, positive, negative. That's our lattice structure, and that is one single layer of a lattice. But this idea is how ionic bonds are, ionic compounds can be solid. I'm going to pass this one around. I'll pass this first. So Alicia's got this great structure. It's a 3D structure, but it's layer after layer after layer of these lattice structures together. My cube's all messed up now. That's supposed to be a cube, but it's layers and layers and layers and layers. What happens if I drop this? Breaks. What's the word for meaning it breaks easily? Brittle. Okay. Ionic structures are brittle, so a salt crystal can be quite large. Who's ever seen like a deer lick, a salt lick for deer? Okay.
Yeah.
It's quite large. But what's the salt that you pour on your French fries?
Small.
Pretty small, right? Well, how did that happen? We shattered it. Okay. So that's what this looks like, kind of up close. And they're passing around once you can hold it. Okay. Turn to the partner next to you and talk about what you notice here.
Dots.
lots of dots. Non-metal stuff, like balance stuff.
So dots get bigger right to left. Come on, Dan. Come in left and right.
All right, 3, 2, 1. Nathan, what does this represent? I know that. You just said it. No, come back to me. Tell me what you just said.
Oh, I said like the right side represents the valence electron. I mean, all of it represents valence electrons, but like the right side of the left side.
Right, so these little dots are how we're representing valence electrons, right? So group 1 has how many dots? 1. Group 8 has how many dots?
8.
Except for helium, because it can't get octet, it only gets up to duet, right? So helium's octet is 2, because it just is so small. So all your metals, which are in blue here, have less than how many valence electrons? Less than
2. Well, no, 3.
Okay, so you got the blue. I'm just gonna stop here. They have less than 4, right? Except for these couple of random post-transition metals that have more than that. But most of our metals are gonna end up making an ionic bond because they are gonna have to lose their electrons to form an ion. But over here we have our non-metals, and they can form either ionic or covalent, right? So a metal and a non-metal can get together to make a what kind of structure? Right, so metal plus non-metal equals an ionic compound. But if I put 2 non-metals together, what do I get? Covalent. Okay? So the idea is that either we're actually exchanging, transferring electrons, or sharing, right? But we will be drawing them with dots now, and these are called Lewis dot models. Who drew these in middle school?
Some
Raise your
guy
hand.
named Lewis.
No, you guys. From your background, who drew these in middle school? A couple of us. Okay. Just seeing where we are, and they're like half the class usually does. Okay. All right. So before I move on to drawing covalent ones, we're going to do a simple example of an ionic structure, and I will be writing this either in my chart underneath ionic or on separate notes that you've been taking already. So the way you address drawing dot structures are, one, write symbols, right? You have to start by writing symbols. This is your thought process. For those of you who have a hard time going, okay, how do I get started here? This is your thought process. Step one, draw the symbols. So with your symbols, though, you're also identifying the number of valence electrons with that symbol. So you'll draw a dot, or number of dots. All right, so everyone should be with me drawing and writing down information. Everybody. Okay? After you've drawn your Lewis dot structure, you have to say, okay, is this going to form an ionic or a covalent bond? That's your thought first. And how would one know if it's going to form an ionic bond? So if it's a metal and a non-metal, or if the number of electrons, valence electrons, are vastly different. Meaning, like, nobody's going to share here. We're going to have to transfer. So here's your first example. I've drawn sodium with how many electrons?
One.
One valence electron. I've drawn chlorine, and I'm adding these together. Okay, I've drawn chlorine with how many? 7 valence electrons. So we have a vastly different number of valence electrons between the two of them. And, like you guys already mentioned, you have a metal and a non-metal. So what kind of bond is going to happen here? Ionic, okay? So that's because what we will now want to show is a dot, the single dot, and this is how what you indicated to me is you draw arrows. So you want to draw this dot being transferred to chlorine. So this arrow is indicating a transfer. So once that happens, here's my end result. I have now sodium, which is now down 1 electron, and how do I show that here?
The plus.
The plus sign, okay? Amelia, you with me? Can you take this with me? Thank you. And I have a lack of 1 electron, indicating a positive charge overall. Garrett, what do I have here?
Octet.
Thanks, Garrett.
You're welcome.
Okay, so you've got octet, and that's going to be indicating all those electrons are now around chlorine. But you have to put the brackets,
Why?
not optional, because you have to indicate something. When you put brackets, you're saying that all these electrons now kind of belong to chlorine. Okay, and that has a -1 charge because what happened to it, Garrett? Right, so this one gained 1 electron, so in that gaining of 1 electron, it has a negative charge now. But collectively, we have overall 1 compound, sodium chloride. This sodium chloride compound as a whole is not positive nor negative, it's what? Neutral. And that's because this +1 and this -1 have now kind of canceled each other out. So can sodium and chlorine ions exist separately? No. By themselves, so that's not going to exist by itself very well, nor is the chlorine. Sodium is going to follow chlorine around like a lost puppy dog the whole time because they're attracted. There's a strong attraction here, simply because of the positive and negative, because positives and negatives attract to each other. That's how it works in chemistry anyway. Okay. So, and the idea is that this can stay together, but in water, they can still dissolve and they can separate some, but they're still close by. They're not like, in Canada and Mexico. They're right next to each other still. Yeah.
Is that why they say opposites attract?
Yes, opposites attract, they say. All right, so I want you to use this idea, and I want you guys to draw one for the formation of magnesium oxide. Same story, symbols, dots, show your process, give me your final.
Wait, who? Oxygen. Oh. I'm so confused. That's not 2, 3, 4. Are you sure? It's not 6 full dots. It's magnesium when it's 12, right? So why would I know this?
How do you find out if it's
Oh, thank you.
so like I should have one where it's like
All right, Courtney, get me started up here. How many dots did you draw for magnesium? Why did you draw 2? Second group, right? So it's in second group, so it has 2. So the group number is the valence electron count. Yes, ma'am.
Does it matter where you put the dots?
Not for me. We're just gonna get those dots on paper. Make sure I can see them. Okay. Mac, how many did you draw for oxygen? 6, because it's in group what? 6. I generally just go clockwise around if you guys are wondering, but here we go. So it's in group 6A. We do sometimes see that it goes 1 through 18, but those are like the B groups when we include those. Josh, what's gonna happen?
you're gonna
So you're going to transfer, try to use our terms, right? So it's going to transfer the electrons over from magnesium to oxygen, and that transfer is now going to allow for magnesium to have a what charge, Gwen?
Positive 2.
Mm-hmm. And then Hunter, what's the charge of oxygen? Say again? -2. Good. So there's 8 dots there, okay? So does oxygen have octet, yea or nay?
Yes.
Yes. Does magnesium have octet, yea or nay?
yeah.
Yes. Okay, let's review why. Look over here on the PR table. Magnesium, when it lost the 2 electrons, who does it now look like? Neon, which has octet. That's why we're allowed to say yes, though it's not listed there, it goes back to its last octet. But overall, collectively, these are what charge? Neutral. Okay? So before I move on, I want you to talk to the person next to you about this yellow question up here. How does this whole idea relate to electronegativity? Good question.
Good question. Yep. B.
Actually, so one component's right. One more
It's a continuum.
track.
Oh, so that's
Yeah, and these ones. Yeah, these ones gated.
All right, back to me. 3, 2,
1.
1. Anishka, help me out here. How does this relate to electronegativity?
I'm not sure. Because, like, not, it doesn't. Just like favorable electronegativity is about electrons, not ion electrons.
So it's more about covalent, but we're going to have a continuum overall of, like, first of all, electronegativity is basically saying, let me, before I say that, put this in your own words. What is electronegativity? This is back from the last unit.
This thing.
I know it's this thing, right? But that's our trend. That's how it we can predict things from that. But what is it?
Attraction to electrons being shared.
So attraction to electrons being shared. Okay? So shared is generally the word we'll use for covalent, right? So if you're looking at magnesium and oxygen, and you got your magnesium over here, and your oxygen way over here, who's more electronegative, guys?
Magnesium.
Oxygen.
So magnesium's high, right? But oxygen's high and right. So who's more electronegative? Oxygen. So if you're more electronegative, that means you're going to take the electrons more often in a bonding situation. Who's taking the electrons? Oxygen, right? So this is all connected back to the stuff we've already learned. Who's willing to give up electrons because they don't necessarily want them as much? Magnesium. It's the same case for all metals. Metals don't really want their electrons. They have less than 8 or less than 4, and that's going to mean that they're more likely to give up their electrons. Draw this one. So you draw your chlorine to chlorine up here first, and then I want you to try for this bottom one. So draw this first for an example, and then try for this one. Josh, tell me what you noticed about this first example up here.
Got electrons on
So, was it transferred?
it. It was transferred.
Was it
Or no,
transferred?
shared.
No, it was shared. Okay, so we're going to try to keep the word transferred for what kind of bonds? Ionic, and the word shared for what?
Covalent.
Covalent. So this chlorine's like, I only need how many more? Electrons. It only needs one more because it has 7 valence electrons, right? This one has 7 valence electrons. How many more does it need? One, because you can see it's just not paired right here. So is this one going to give it up over here to this one?
No.
Is this one going to give up to this one? No. So instead they just keep them in the middle and they keep them in between both of them. Okay, so everyone put your pencils between the two, put both your pens or pencils between you guys at your desk. If you don't have a partner, then I'll pretend. Okay, put both your pencils there. There's two pencils there, right? All right, so the person on the left, take both pencils. Okay,
I got back
so
up.
hold up your hand if you are a positive charge. It should be this side. So if you took both pencils, pencils represent electrons. My bad. Pencils represent electrons. Hold up your hand if you're positive charge. All right, hands down. Put your hands up if you are a negative charge. Okay, so this was an ionic situation, right? So we literally transferred the electrons to one person. Pencils back in the middle. Okay, now each person pick up one electron. One pencil. Okay, that's you guys equally sharing, right? Okay, pencils back down. So that example I just did, the equal share, that's called non-polar covalent. Non-polar covalent. Now, both of you guys hold the pencils at the same time. Both pencils. Okay.
Covalent.
Okay, and the person on the right, just tug them towards you a little bit more. Person on the right, tug them towards you a little bit more. Okay, so I am not equally sharing on when she is struggling over here. I am really trying to pull the electrons from her, but I'm still holding on. Like we're both still holding them, right? We're both a covalent bond. We're both holding it, but I'm more greedy, so hence I'm more negative because I want the electrons over. She won't give them up to me, so like I have to share, but I don't want to. So we're holding that. Now go back. Now let the other person be more electronegative. Okay, but we're still covalent, right? She's just pulling it away from me. Okay, back in the middle. Okay, so the situation we just did now, okay, release, bring your pencils back to the original owner. Okay, what we just represented was something about polarity. We're going to have a bond polarity in a second, okay? But let's make sure we understand this. In this situation, did the electrons get pulled to one side or the other, or were they shared equally? Okay, so these were shared equally because they had the same electronegativity. So the electronegativity of this one equaled the electronegativity of this one. So before I move on to more electronegativity examples, look at the new periodic table I've laid on your desk. It looks like this. Okay, do not take it, thieves. I see you eyeballing it. Go and take a picture of it so you don't have to take it from me. Oh my goodness. Usually I copy things on colorful paper or laminate them, but I didn't, so sorry. I just see stuff that mine is there. Okay. Look at the electronegativity value for chlorine. What does it say? Electronegativity value for chlorine. 3.0, right? You with me, Nathan?
Yes, ma'am.
What's the electronegativity for chlorine?
It's the number under it.
3.0. Okay, so the electronegativity value is 3.0 and 3.0. So there's no difference in terms of their electronegativity. So they're going to equally share the electrons. Okay. That's basically what you're picking up from here. And you will always get this if needed, okay? So whenever you need it, I'll make sure you have it. So, Alicia, tell me what you drew for hydrochloric acid. H with 1 dot plus with 7 dots. Will pick up from here.
You add, or you draw an arrow from the whole dot to the CL.
What word would I be using for if I were drawing an arrow?
Transfer.
Am I transferring?
Yes.
Share.
Do you? I could transfer, but I would be making ionic bond. What are
You want to
these?
share it?
We're gonna share it. Okay, we'll talk about why that is in a second. So we're gonna just kind of bring these together, kind of collect them together by smushing them together. So how do I draw this now?
You do H dot combined with the CL dot and then
Okay.
6 other dots.
Okay, so I'm drawing this now with the bond, with the 2 electrons kind of smushed between them, just to say, hey, I'm in the middle here. So if I circle hydrogen, how many electrons are around hydrogen? 2. Is that cool? Is that good? Is that stable? That is the duet rule, right? If I circle chlorine, how many electrons are around it?
8.
8 valence electrons, and is that cool?
Yeah.
Yeah, that's offset, right? Okay, so both of them are happy. Okay, that's the happy. So that means that they're both stable. But the reason they're stable is because we're actually sharing electrons. Now, before I go on to some more examples, let's look at our electronegativity chart. Look at hydrogen. What is hydrogen's electronegativity number? 2.1 for hydrogen. Okay, what is it for chlorine? 3.8 for chlorine. Math. Subtract these. It's going to be absolute value. Subtract these.
0.9.
0.9, right? So the change in electronegativity, or the difference in electronegativity is 0.9. Look down on the chart down here. Where does that fall in my category? It is polar. Does everybody see that? Help the person next to you. Do you see the category? Polar covalent. So it's a covalent bond, right? It's sharing, but the word polar means that one side was more electronegative. So much that it actually creates a disruption to the charge here. So basically, I'm going to redraw this over here. Chlorine is more or less greedy for electrons. More. So these electrons that are hanging out here, plus these electrons that are here, when I draw a line, it actually means 2 electrons. So a line means the same as this. The electrons are just being pushed, or actually pulled, towards chlorine more. So we draw like an arrow to indicate that. Which scenario is that with the pencil grabbing thing? Okay, so go ahead and demonstrate that again for me. Pencils in the middle. Okay, equal sharing, calm, collected, smile at the person next to you, right? Now, polar bond. You can be polar. Oh my gosh, okay, so the electrons are being scooched towards one side, but we're still sharing. But one person is more greedy. Okay. Yes.
What happens if I win?
If you win, it's an ionic bond, and you guys, he follows you on like a lost puppy dog. Okay? So, 1 second. So what I've drawn here is that polar situation where this side over here has a partial, look at how I'm drawing this. Partial, it's like an almost 8. Look up here. Partial is an almost 8. Okay? And we put a negative sign on that to indicate this side over here is partial negative. We can't finish the 8. This side over here is partial positive. This is a lowercase sigma. It's a Greek symbol. It's got that little, like, almost 8 thing. Okay? It almost does, yeah. So this is a polar covalent bond. All right. Open up your computers. I'm going to tell you, you're going to read something before I move on from here. What was your question?
Why are some of them blank?
We're going to talk about that in a second. Okay? Open up your computers and get logged on, and I'll tell you where you're going. Slackers, so you can grab a computer. That was warm up. That was warm up.
I didn't even turn mine on.
Get it on. Get it on. All right, so once you're getting pulled up, do I need to go back for anybody? Rashida? Here. All right, so once you get pulled up, just go to my website, go to homework, just Jessica and Lo. It should pop up. Google Jessica and Lo, it'll come up. All right, so before I move on, somebody asked me why on here are some of them, why do some of them have no values? So I'm gonna scooch forward real fast.
Because you don't want to have one.
Say again? Well, they do already have octet, right? So octet is stable, right? If I have octet, do I have to bond with somebody?
No.
No. So who, like, basically will never bond?
Helium.
Helium, neon, and argon. Okay, the top of the noble gases will not bond because they like, no, I get no extra benefit from this. You guys are just trying to get my electrons. I don't need to bond. I am perfect in all ways. But krypton, xenon, and radon, they actually are a little bit more friendly of the noble gases. Though they have octet, they're willing to share with other folks, others that are coming in. So that's why they actually do have a value. So those top ones will not bond. Okay, we're gonna get back to this in a second. You're on my website? Close enough? Why? What's going on? Okay. So I'll show you guys where you're going and then you guys can start, okay? So under homework, I just put the classwork links there so it's just easy access. So it says, read the polar bears article first and then answer questions with a partner. Then the molecular polarity simulation questions can be on the same page. But I want you just to first start off by reading this polar bear comic. This is the cutest comic in the world, point one. And two, it lets you see the polarity in a little bit of a different light. So the first reading, I just want you to sit and read quietly. But it looks like, oops. It looks like this at first. Scroll down to where the comic begins, which is not here, 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 not here. Okay? That's where you're starting to read. And just read first for a little while. You guys can zoom in and make it bigger too, so I can see. Quietly read. Walked in on videoing, so you guys can take the notes down, but just pick up where we are by talking to the person next to you. What page is on? 89? It's on page
91.
Okay, I'm just seeing where you guys are. Continue, go read the whole thing, okay? Come back to me. I know you're close in the middle part of it. So I want you to write down these few pieces of information before you move on to the rest of the day, okay? So I know that you guys are reading and you're like, okay, pick up a little bit. Just kind of picking up what they're putting down. Okay, so the electronegativity side is pretty key here. Okay, so draw a continuum. That was a word they said in there, a continuum, which is a continuous kind of trend. And I want you to label one side no electronegativity difference. And I want you to label the other side a huge electronegativity difference. So just draw this on your notes that you've kind of been working on already. No electronegativity difference, huge electronegativity difference. And I want you to put in the middle and like medium electronegativity difference. I think Parker asked me this earlier. He said, what if I just take the electrons from the middle? What if I just rip them away? What did I say that, what kind of bond did I say that was?
Ionic.
Ionic, right? So who would have the ability to just rip the electrons away? A huge electronegativity difference, right? Oxygen's like, come here magnesium, those two electrons, those are mine, right? They actually will swipe them from you. So put ionic on this side, ionic bonds, which are going to be indicative of usually a metal, non-metal, and a large electronegativity difference. So what do you guys want to label over here? So covalent comes in two flavors, okay? Non-polar covalent or polar covalent? Non-polar, good. Non-polar covalent, meaning how do they take their, how do they bond with electrons? Say again?
They share equally.
They share equally, right? So in the pictures over here, the sharing equally situation came in, well, here, first of all, what kind is this one?
Polar.
Polar, right? So the bears totally swipe the electrons or the scoops of ice cream. Here, they're trying to show how the electronegativity trend is a big idea behind the bonding. Let me actually get to the part. Here we go. So what are they doing here? Sharing equally, right? So the sharing equally is going to be a non-polar. Electrons equally. That's a non-polar situation, meaning no side is more charged than the other. What about here? In the middle, right there.
One side is.
One side is what?
Pulling on the other.
So the bear or the penguin's pulling more on the electrons?
Both.
Who's pulling more?
It's equal.
I have to have the flu vaccine. There we go. It's my quick reminder for myself. There's my calendar. I haven't gotten it in years, but I was told I should. So let's see if I get the flu this year, guys. I'll tell you. Okay. I probably got it in like 2 decades. 1 second. Let's go back to this. Alexia, tell me again what who's has more of a share of the electrons? The bear, right? The bear, right? And how are we indicating that here? Do you see which way the arrow is pointing?
The arrow's pointing to the right.
The arrow points towards the negative region. The arrow points towards the negative region. Doesn't this side over here look like a plus sign? Yeah, right? So that's supposed to indicate the more positive end. So we actually would put a partial positive and a partial negative on that. But what I want you to see there is it shared equally? No, okay? So we're going to have our polar covalent region here in the middle, where there's a medium electronegativity difference, and they are not sharing electrons equally. So it's an unequal sharing of electrons, which creates that arrow thing that we're drawing to indicate that. Yes, ma'am? Oh, yes, go back. Thanks. Okay, so on this image, the electronegativity differences are so large, that's when we kind of discounted with the ice cream and it's gone, and the electronegativity, or the bear has now created a more negative region on that side. Okay, how does this play into what we have here? Do you see the differences that I've created, or the electronegativity difference indicated on this little chart? So when I say no electronegativity difference, it's actually a continuum. From 0 electronegativity difference up to what is nonpolar? Some people's might be a little different, but what's it say generally? 0.39, 0.4, some people have like 0.5, so it's a continuum, so we don't have a great idea what that is. But from about 0 electronegativity difference to 0.5-ish is going to be generally nonpolar. Okay, what's the value differences for the polar region? 0.5 to what? 1.69-ish. It's a medium electronegativity difference. But then once we get above 0.69 or 1.69, so 1.7 and up, it's going to be in the ionic region. Like I said though, it's a continuum, so we have some fuzzy areas in between. And that's why we just draw on kind of a line, and we'll be using this more tomorrow. Okay? Flip modes, go back to my website. And I just want you to play with this first to see more of what we're talking about, like in action. Go to the other link where it says FET molecular polarity sim, write down conclusions. Let's just get to the point where we can view it first. So when you're looking at this, it gives you a little background information. I want you to read that. You see the paragraph? Read that first. And I do want you to summarize it, but if we have to do some of this tomorrow, that's cool. Visit the link, and I want you to play with this and see how you can change electronegativity, polarity, molecular polarity, and bond polarity. So literally play. You have 10 minutes. Okay?
Yeah.
I want you to start to look at the questions there as soon as you get an idea of how this works. Go to first two, the last one you have to do.